Our presenter today is Dr. Julian Barnes. Julian is a Principal Science Expert at Shell Technology Center in Amsterdam, the Netherlands. He has held a number of R&D positions in different areas of Shell and in different countries, including the United Kingdom, France, Japan, Germany, and of course now the Netherlands. He has published widely and holds a number of patents, and is currently Shell's global specialist on surfactants across home care, personal care, and industrial applications. And with all that, he does find time to volunteer with AOCS as a chair. So he will present his poster today. If you have questions, we will answer those at the end of the presentation. And you can write those in the question panel of the control panel of the webinar. You can also use the chat feature, and we will answer those at the end. As a reminder to those who have joined us just a little bit later than the start, I did put a direct link to the ePoster in the chat box so that if you would like to view that on your screen, that you can. So thanks again for joining us. And with that, I will turn it over to Dr. Barnes.
Thank you very much, Amy. Right, for those who can see me, first of all, to start, you can probably see my video here. So the chairs at the back are because it's our study and that we have people around for dinner. So in case you're wondering why I've got chairs stacked behind me, let's get to it. So I'm going to show the full screen and the poster. Hopefully this will work. Right, can everybody see? Let's get rid of my. Can you see my screen, everybody? Can somebody confirm that they can see the poster okay?
So this is Amy, and yes, we can see the poster. So I think you're good to go, and I would just zoom in on each section as you present, just as if you were presenting it in. Yes.
Brilliant. Thank you. Okay, thank you very much. Right, we're all set. I first of all want to acknowledge my co-authors of this paper. So this is a Shell paper, both chemicals and Shell upstream. So there are a number of people, myself, Diederik van Bassenberg, Jeff Southwick, Carl van Rijn, Sebastian Pertiz, F. Kaiser, Mark Brewer, and Tim King. And it's basically based on work we've been carrying out over several years, and this is the more recent phase of that work that we've been carrying out. And the subject basically is about alcohol alkoxy, particularly alcohol propoxy sulfate surfactants, which are very good candidates for enhanced oil recovery. And we think this study that we've done actually is going to change the paradigm for the use of alcohol epoxy sulfates in enhanced oil recovery projects. And I'll explain a little bit more what I mean by that. Why are alcohol epoxy sulfate surfactants important? Well, they have three basic points. Firstly, that they give you an ultra-low interfacial tension between the oil and the water, which is essential for an enhanced oil recovery surfactant. You need that ultra-low interfacial tension and get what's termed a microemulsion, which is an indication that you're getting that ultra-low interfacial tension. And that gives you high oil recovery. The second is they're very tolerant to divalent ions, calcium, magnesium mainly, being the divalent ions. And these ions can be very high in the subsurface in reservoirs. So surfactants such as LAS or eternal olefin sulfonate are not tolerant to those sorts of magnesium and calcium ions and precipitate, whereas the alcohol epoxy sulfate stays in solution, so it's soluble in the presence of those ions. And the last point, the third point basically, which makes alcohol epoxy sulfate surfactants important, is that they are relatively straightforward to manufacture at large scale and are cost effective. And both of those points are essential for a surfactant for use in enhanced oil recovery. you need something which is obviously cost effective, and the volumes that are required for large enhanced oil recovery projects are very large. And these are basically cost effective surfactants. And they're more cost effective than, for example, the alcohol-based sulfonate, which is not a straightforward surfactant to manufacture, and the alcohol-based carboxylates. So that's what makes the alcohol propoxy sulfates so attractive. But the limitation, which is in this point here in the poster, the limitation is their thermal stability. Basically, they have a sulfate bond, and that sulfate bond will hydrolyze, particularly in the presence of acid, so it's acid catalyzed. That is affected by high temperature. So basically, it's all about kinetics. You have a faster hydrolysis rate at high temperatures. And the conventional wisdom has been that 60 degrees Celsius, there was some very work done a long time ago looking at alcohol sulfate, showing that 60 degrees Celsius is about the limit to which you can keep the alcohol propoxy sulfate stable. So beyond 60 degrees Celsius, it will decompose. The other point is, though, that oxidation plays some role, which I've made noted points here, that if you have oxidation occurring, that's another mechanism for the decomposition of alcohol propoxy sulfate. And that's a key point, that you can have the oxidation of the alcohol propoxy sulfate, particularly the PO chain of the sulfate, combined with hydrolysis, and that will actually give you even further decomposition. So that's basically an overview of introduction. The past work that we refer to in this paper is shown here in this part of the poster. We used, actually, there are several references we put in here, but the one that's the grounding paper is dating back to 1988, which is by Larry Tarley from Exxon. So that was quite a comprehensive and very systematic look at the stability of alcohol propoxy sulfates at different temperatures in the presence of different ions, different salts. And we've used that paper as a starting point for our work. There are some other references we've put in here as well, which you can refer to if you like. The thing about our study, which is we think are different from previous authors, is that we use this equipment here that there's a photo shown here, where we prepared all the samples in tubes, so all the aqueous solutions in tubes, and put those tubes in ovens, all in a nitrogen glove box, a very large nitrogen glove box, which you can see here. We did this because we had earlier work that was carried out. As I said, this was part of a long-term study over the years we've been carrying out, and we had some anomalous results, which we thought were due to not excluding oxygen. So as I said, oxygen is a bad actor. If you can exclude oxygen, you'll have better stability of the alcohol propoxy sulfate. So we, as far as possible, excluded oxygen entirely from this study by using this glove box for preparation of the tubes, and for the 12-month that the ovens are inside this huge glove box, so everything's under nitrogen. Bear in mind that in the subsurface, it's fully anaerobic condition, so oxygen is not present in the subsurface. So what we're trying to do here experimentally is get as close as possible to the subsurface conditions with exclusion of oxygen. The other part of the study that we've done, which is noted here in point 1 of the experimental, is that we've, as far as we can tell, this is new, we haven't seen this in other experiments, we've looked at the stability of this surfactant type with and without the presence of reservoir rock. So we use crushed reservoir rock in half the tubes that we set up for this stability work. And the reason we did that is reservoir rock is a huge surface area, and basically can stabilize the pH of the solution subsurface. And if you can stabilize this pH and keep it above 7, which all the data suggests that's true, then you will have like an in situ pH stabilization of the alcohol propoxy sulfate. So it won't go low in pH below 7, and you won't get this acid catalyzed hydrolysis of the sulfate bond. So we think that when we started these experiments, we thought that the reservoir rock will stabilize the alcohol epoxy sulfate compared to without the reservoir rock, and that was one of the purposes of the work. So we made these solutions. We made lots of little tubes, which we would open at various points during the 12-month period. So we didn't use one large stock solution and then take samples because we didn't want to get contamination. We just had several tubes which we opened, took a sample, analyzed it, and threw it away. And then the next tube, a month later or so, would be used. And we looked at the tubes we looked at solutions in terms of pH, concentration total of surfactant by percent active titration. And we've also carried out some looking at the discrimination of the different surfactants by LCMS. But the work I'm showing you here will be about the pH measurements and about the concentration of the surfactant by percent active. So we'll go to the results. There were 3 pairs of results. They're all the same. They're all the same experiments, but we just have different charts showing what we're measuring. So we've got the tubes which are with no rock, and we've got the tubes with rock. And this is the pH. These are the pH plots for 80 degrees Celsius and 105 degrees Celsius. And you can see that with no rock present, the pH stability is poorer for the 105 degrees Celsius. For the 80 degrees Celsius, with and without rock, both are pretty stable. But you can see the presence of rock does give us that pH stability, which is what we would have expected. So that's positive. That suggests the presence of rock could be a mechanism for keeping the alcohol epoxy sulfate stable, because it's keeping the pH stable and we're not going below 7. Now, when we then looked at the surfactant concentration measured by percent active, and this shows the surfactant concentration as a function of it starting 100% active. And as you can see, the tubes that we were looking at were a mixture of the sulfates alone, like the 13-PO sulfate, if you can see here on the labels, 13-PO sulfate, 7-PO sulfate, and then the same with an alpha-benzene sulfonate, and the same with an internal film sulfonate. So what we saw was that thermal stability-wise, at 80 degrees Celsius, they all look good. That with and without rock, they all look pretty well stable, well above 80%, for with and without rock. I think that's not a lot of difference between these two. I know there looks to be a small difference between the left and right, but I think they're all approximately the same. Then when you go to the 105 set, so it's the same measurement we're showing here, the relative concentration with and without rock. You can see that with no rock present, they all basically decomposed pretty rapidly. So within a few months, up to within about 4 months, they crashed down to 0, and then basically we didn't have any surfactant present. Whereas with rock present, at 105 degrees Celsius, we were getting stability up to about, let's just say, 8 months, 8 months or so, and then it decreased. So what this is showing, that even at 105, which is a very hot temperature, the alcohol epoxy sulfate is staying reasonably stable, and it's not diving. You're not getting this over a cliff instability. I think that's what I wanted to say. Yes. So coming back to going to the conclusions. You can see this. Yeah, this gives you a little bit more about the. Yeah, okay. Maybe I should make a mention, if it's in the poster, the brine that we used for the solutions that we made was 1.5% TDS with about 160 ppm divalent ions. That was representative of the brine that we were using in a particular project, and we didn't have any sodium carbonate present or other buffers, so it's just a brine present yeah, basically. So we think these results are very important, and we think it just changed the paradigm. The paradigm being that alcohol epoxy sulfates are not sufficiently stable above 60 degrees Celsius. You can see that we're getting stability at least up to 80 degrees Celsius. And even at 105 degrees Celsius, we're getting stability up to about 8 months, and then it decomposes, then it decreases. And the key to these experiments, which are representative of the subsurface, is that we exclude oxygen as far as possible in the lab experiments, and we've used reservoir rock, which will always be there in a large surface area as a pH stability mechanism. So thank you very much for your attention. I'd be very pleased to see if I can answer any questions.
Thank you. If you do have questions, please use the question box in the control panel, and we will answer those here shortly. I do have a question, and this one I'll take, is I believe it's about the certificate of attendance for the webinar. And so all registrants will receive, should go out tomorrow, a certificate of attendance as well as a copy of the recording, and those will go out via email, just like your registration confirmation did. So you should have those tomorrow. If not, get in touch with me and I'll make sure you get those. Okay, so we do have one question in, and it is, can you describe the method how the surfactant concentration was determined by surfactant titration?
Yes, we used a pretty industry standard method, which is a single phase potentiometric titration. It's used basically not just in this area in enhanced oil recovery, but used for surfactants in general. And you typically use hyamine, which is a cationic, to titrate the anionic surfactants. These are sulfates to form a complex, and you measure that through what's called potentiometric titration. I can give you more details if you like, or you can just Google it. It's a pretty standard method for measuring surfactant concentration for anionic surfactants.